Okay, we're going to continue the discussion on waves and oscillation. Last time we had a few different quantities we needed to know about. Frequency, for instance. F. Wavelength. Was lambda. And we had the velocity of a wave is related to these characteristics through the equation. Velocity is frequency times wavelength. And we also saw the period of oscillation, similar to frequency, is t, and it was defined as 1 over the frequency. And we had wave number, k, and it was defined as 2 pi over lambda. And we also discussed the mathematical formulation of a wave, y, that is the height of a wave or the amplitude of the wave at some time t, is given by a, the amplitude, the maximum amplitude of the wave, sine of omega t minus kx, where omega is also called the angular frequency, is 2 pi times f. Now, I want to continue talking about waves and oscillations today. One other equation I should let you know about is the equation which characterizes the motion of a pendulum. So if you have, let's say, a ceiling pendulum, and that pendulum, of course, can swing back and forth. This pendulum, let's say it's made of a string with no mass. It's just a perfect string whose length, L. And the pendulum has a mass at the end of it, and that's called the pendulum bob. And we could say we start this pendulum off by moving it over a certain angle theta. The question could be asked, what will be its frequency as oscillation? As it moves back and forth, it'll oscillate back and forth. We may want to find out what's the period of oscillation, what's the frequency of oscillation, and so forth. Well, it turns out that in order to answer this type of question, we only need a few pieces of information. It's surprising, but the period of oscillation t of a pendulum is given by 2 pi square root of L over G. Where, as I said, L, that's the length of the pendulum, and G, that's just 9.8. So surprisingly, the only thing that affects the pendulum's frequency and period, that is how fast it moves back and forth, or how many times it moves back and forth per second, is how long is the pendulum, and what kind of gravity does the pendulum exist in? Are we on Earth? Are we on the moon? And so forth. It doesn't matter how heavy the pendulum bob is. It doesn't matter how far from the equilibrium point you draw it back. All of that stuff gets canceled out, and the only thing that determines the period and the frequency of oscillation is the length of the pendulum and gravity itself. So, let's look at a few examples of what we did last time. And we'll start with an example about pendulum. So, from the sample questions I had posted on Canvas, we have a pendulum with a string length of 1 meter is lifted to an angle of 30 degrees. If the pendulum bob has a mass of 2 kilograms, we could find out what is the period of oscillation. Well, as we just saw, the period of oscillation for a pendulum is 2 pi square root of L over G. So from the problem, we have 2 pi times the square root of L, which is 1 in this case. G, we're assuming we're on Earth, so it's 9.8. And we get 2.007 seconds. So that means if I pull this pendulum back and I let it go, it'll take about 2 seconds to oscillate one time. Part B asks us to find what is the frequency Well, this isn't so bad. We already know a relationship between period and frequency. The period is 1 divided by the frequency. So frequency then is 1 over the period. So 1 divided by 2.007 gives us 0.498 hertz. All right, and then lastly, we could ask how many times will the pendulum make an oscillation in 10 seconds. Well, to figure this out, we just have to realize what the period of oscillation means. The period means how many seconds it takes to make one oscillation. So if we know it takes 2 seconds to make an oscillation, and we want to know how many oscillations will it do in 10 seconds, then we just say 10 seconds divided by the period, which is 2.007, and we get that this pendulum will make 4.98, so we have to say 4 oscillations. Obviously, if we want to know the total, how many total oscillations, 0.98 is not a full oscillation, so it'll make 4 full oscillations in 10 seconds. The next example we had, we have a spring oscillator. So if a spring oscillator of mass 2 kilograms is set into motion and we know the frequency is 100 hertz, then we can ask A, what is its period? All right, well, first to find the period, again, we just use a relationship that period is 1 over frequency. So since I know the frequency, it's 1 over 100, which is 0.007. 0.01 seconds. So that is, it takes 0.01 seconds to make one oscillation. Now, just for your own information, just so you could get a picture of what a spring oscillator looks like, let's say here's a wall, here's the floor, here's a spring, and attached to the spring is a block. And the block has a mass of 2. And basically you pull the block and then you let it go and it oscillates back and forth like that. And so for this particular situation, we're told the frequency of oscillation is 100 hertz, so it'll take 0.01 seconds for this block to move back and forth one time. Now for part B, this is tricky, as we need an extra piece of information. We need an equation for this. This question says, what is its spring constant? So you remember spring constant from physics 1, where we did conservation of energy. We had a spring in our problems, and the spring can have a certain stiffness, K. That's the spring constant. So K is what I'm looking for here. And I want to know, if the frequency of oscillation is 100 hertz, what must be the spring constant of this spring? Obviously, in order to do this, we need an equation, like the pendulum equation, which relates frequency or period to the variables related to a spring, like its mass or its spring constant or how far you stretch the spring and so forth. So, I know the frequency of a spring oscillator is given as 1 divided by 2 pi square root of K over M. So for this equation, K, that's the spring constant. And M, that's the mass of the block. Sometimes, of course, you'll see the period is 2 pi square root of M over K, because people don't like 2 pi in the bottom. So we want to use this equation to solve for K. So let me just get this one out of the way. Using our frequency equation, I want to solve for K, so let me square both sides to get rid of the square root. So that tells me frequency squared is 1 over 4 pi squared times K over M. All I did was square both sides. Now I want to get K by itself, so I multiplied by 4 pi M, 4 pi squared times M, I should say. So the 4 pi squared cancels the 4 pi squared, the M cancels the M, but then I have to do it to this side too, 4 pi squared M, and I get K is 4 pi squared M F squared. And now all I have to do is plug my numbers in. 4 pi squared. The mass of the spring oscillator was 2 kilograms. The frequency was said to be 100 squared. And so, plugging these numbers in, we get 7.9 times 10 to the 1, 2, 3, 4, 5. A very stiff spring. But again, it starts with this equation right here. You'll find it on the formula sheet, of course, or maybe the period version. I'm not sure which is there. But again, once we know the equation, we take the numbers out of the problem, stick it into our equation, solve for the appropriate variable. Here we wanted K, so I brought everything to one side of the equation, left K by itself, plugged in my numbers, and I get a value for that. All right. Now this third question, this is a nice one because it kind of relates what we're doing now to conservation of energy from before. So let's go through that really quick. We have a spring oscillator again. Of mass 1 kilogram is stretched by 5 centimeters if the oscillator takes 100 seconds to complete 10 oscillations. We want to calculate a few things. So first, we want the frequency. All right, so, well, in order to get the frequency, what do I know? I'm told the oscillator takes 100 seconds to do 10 oscillations. So if it takes 100 seconds to do 10 oscillations, then 10 over 100 tells me it'll do 1 oscillation in 10 seconds. Okay, so the total number of oscillations over time tells me 1 oscillation can be done in 10 seconds. That means the period of oscillation is 10 seconds. And the frequency is 1 over 10 seconds. Just to make sure that's clear, I know it's like saying I went 60 miles and it took me 2 hours to do it. Well, that means what's my speed? 60 miles in 2 hours means I did 30 miles in 1 hour. So my speed would be 30 miles per hour. Here I did 10 oscillations in 100 seconds. So that means I could do 1 oscillation in 10 seconds. And understanding what that means, the number of oscillations per second, that's the frequency, and the number of seconds it takes to do 1 oscillation, that's the period. So here, frequency is 1 over 10. Part B, we want to know what is the period. We just found that out at the same time. Period must be 10 seconds. All right. Part C, we want the spring constant. Okay, well, just like the previous example, we know. So we had the equation, the frequency of a spring oscillator is 1 over 2 pi, square root of k over m. And we saw, rewriting it, solving for k, we got k was 4 pi squared m f squared. So 4 pi squared. The mass for this problem, we're told the spring oscillator has a mass of 1 kilogram. The frequency we found was 1 over 10 squared. And we get the spring constant K is 0.395 in this case. All right. The next example, or the next part, we have D. Calculate the maximum potential energy. Now, to get this, we have to remember back from General Physics 1, the potential energy due to a spring was 1/2 kx squared. So to do this, of course, we need the spring constant k, but that we just found, that was 0.394, or 395. X, that's how much the oscillator, the spring, is stretched, and we're told it's stretched by 0.5 centimeters. And I know we have to convert this. Centimeters is bad units. We need meters. So it's 0.005 meters. So plugging this stuff in, we get 1/2. K is 0.395. X 0.005 squared. And we get 4.93 times 10 to the minus 6 joules. Part E, maximum kinetic energy. Well, again, this is something having to do with conservation of energy. We know that the total energy must remain constant, and as this spring moves back and forth, when it's stretched as far as it'll go, it's got no kinetic and pure potential. And then as it becomes unstretched and gets back to equilibrium, all the energy that was potential energy is now kinetic. So I know the max kinetic must be the same as the max potential energy was. Thus, I don't even have to do any calculations. The maximum kinetic must be the same 4.93 times 10 to the minus 6 joules. Part F, what's the maximum velocity? Well, I know the equation for kinetic energy. That's 1/2 mv squared. So, I want to solve this for v. The maximum kinetic, 4.93 times 10 to the minus 6, is equal to 1/2 the mass, but we were already told the mass is 1, times v squared. So solving for v, we get 0.003 meters per second. All right, part G, we want the potential energy at the halfway point, the 50% mark. So basically what that means is, if we have our spring and our mass, we stretch it. The most we stretch was 0.005 meters to here. We want to know, what about when it's halfway to there? So of course that point is going to be 0.0025 meters. So that's going to be the point where we're going to calculate our potential energy and our kinetic energy. So the potential energy at the halfway point, again, is 1/2 kx squared. K, again, that's our 0.395. X, that's the point how far we've stretched it, we're told we're stretched to 0.0025. So, plugging these into our calculator, we get 1.23 times 10 to the minus 6 joules. So, we stretched it out to maximum length of 0.005. We let go, and then at the 0.0025 mark, we measure its potential energy there. We find it to be this number, 1.23 times 10 to the minus 6. Part H says, all right, what's the kinetic energy there? Well, if we remember our previous maximum potential energy was 4.93 times 10 to the minus 6. And the potential energy at this point was 1.23 times 10 to the minus 6. So the difference between these two is how much energy it lost from potential, and thus it's how much energy must have been put into the kinetic. So I just take 4.93 times 10 to the minus 6, I subtract off 1.23 times 10 to the minus 6, and I get the kinetic energy at this point must be 3.7 times 10 to the minus 6 joules. Lastly, part I want to know what's the velocity. How fast is this block moving at this 50% mark, at this halfway point? Well, again, we have the kinetic energy at the halfway point, and that's equal to 1/2 mv squared. So, the kinetic energy, 3.7 times 10 to the minus 6, is equal to 1/2 the mass, 1 kilogram, times the velocity, which is what I want. So velocity at the halfway point must be 0.003 meters per second. It's actually 0.0027. And that's how fast this block must be moving at that halfway point. I put 0.0027 because if we look back, the velocity, the maximum velocity this object had was 0.003. And I know if we're not quite there, we're only at the halfway point, our velocity must be less. And if I just round the number to 0.003, you don't see it. But if we look at the number not rounded, we can see obviously 0.0027 is a little bit smaller than 0.003, so it does make sense. All right, so I hope this helped you understand the practice problems that were posted. We will continue with this later.